In programming language theory, lazy evaluation, or call by need, is an evaluation strategy which delays the evaluation of an expression until its value is needed and which also avoids repeated evaluations. The sharing can reduce the running time of certain functions by an exponential factor over other non-strict evaluation strategies, such as call by name. The benefits of lazy evaluation include performance increases by avoiding needless calculations and error conditions in evaluating compound expressions, the ability to construct potentially infinite data structures, the ability to define control flow as abstractions instead of primitives. Lazy evaluation is often combined with memoization, as described in John Bentley's Writing Efficient Programs. After a function's value is computed for that parameter or set of parameters, the result is stored in a lookup table that is indexed by the values of those parameters. The next time the function is called, the table is consulted to determine whether the result for that combination of parameter values is already available. If so, the stored result is simply returned. If not, the function is evaluated and another entry is added to the lookup table for reuse. Lazy evaluation can lead to reduction in memory footprint, since values are created when needed. However, lazy evaluation is difficult to combine with imperative features such as exception handling and input-output, because the order of operations becomes indeterminate. Lazy evaluation can introduce space leaks. The opposite of lazy evaluation is eager evaluation, sometimes known as strict evaluation. Eager evaluation is the evaluation strategy employed in most programming languages. History: Morris and Daniel P. Friedman and David S. Wise. Applications: delayed evaluation is used particularly in functional programming languages. When using delayed evaluation, an expression is not evaluated as soon as it gets bound to a variable, but when the evaluator is forced to produce the expression's value. That is, a statement such as x equals expression clearly calls for the expression to be evaluated and the result placed in x. But what actually is in x is irrelevant until there is a need for its value via a reference to x in some later expression whose evaluation could, itself, be deferred, though eventually the rapidly growing tree of dependencies would be pruned to produce some symbol rather than another for the outside world to see. Delayed evaluation has the advantage of being able to create calculable infinite lists without infinite loops or size matters interfering in computation. For example, one could create a function that creates an infinite list of Fibonacci numbers. The calculation of the nth Fibonacci number would be merely the extraction of that element from the infinite list, forcing the evaluation of only the first n members of the list. For example, in the Haskell programming language, the list of all Fibonacci numbers can be written as fibs equals 0, 1. Zip with fibs in Haskell syntax prepends an element to a list, tail returns a list without its first element, and zip with uses a specified function to combine corresponding elements of two lists to produce a third. Provided the programmer is careful, only the values that are required to produce a particular result are evaluated. However, certain calculations may result in the program attempting to evaluate an infinite number of elements, for example, requesting the length of the list or trying to sum the elements of the list with a fold operation would result in the program either failing to terminate or running out of memory. Control structures in many common, eager languages, if statements evaluate in a lazy fashion. If a then be else C evaluates, then if and only if evaluates to true does it evaluate, otherwise it evaluates. That is, either or will not be evaluated. Conversely, in an eager language the expected behavior is that define f equals 2 asterisk x set k equals f will still evaluate when computing the value of f even though is unused in function f. However, user-defined control structures depend on exact syntax. So for example define g equals if a then b else cl equals g and would both be evaluated in an eager language. while in L equals if H then I else J or would be evaluated, but never both. Lazy evaluation allows control structures to be defined normally, and not as primitives or compile-time techniques. If or have side effects or introduce runtime errors, the subtle differences between and can be complex. It is usually possible to introduce user-defined lazy control structures in eager languages as functions, though they may depart from the language's syntax for eager evaluation. Often the involved code bodies need to be wrapped in a function value, so that they are executed only when called. Short-circuit evaluation of Boolean control structures is sometimes called lazy. Working with infinite data structures, many languages offer the notion of infinite data structures. These allow definitions of data to be given in terms of infinite ranges, or unending recursion, but the actual values are only computed when needed. Take for example this trivial program in Haskell. Number from infinite list. Int to int number from infinite list n equals infinity. N1 where infinity equals 1, main equals print $number from infinite list 4 in the function number from infinite list. The value of infinity is an infinite range, but until an actual value is needed, the list is not evaluated, and even then it is only evaluated as needed. List of successes patterned other uses in computer windowing systems. The painting of information to the screen is driven by expose events which drive the display code at the last possible moment. By doing this, windowing systems avoid computing unnecessary display content updates. Another example of laziness in modern computer systems is copy-on-write page allocation or demand paging, where memory is allocated only when a value stored in that memory is changed. Laziness can be useful for high-performance scenarios. An example is the Unix mmap function, which provides demand-driven loading of pages from disk, so that only those pages actually touched are loaded into memory, and unneeded memory is not allocated. MATLAB implements copy-on-edit, where arrays which are copied have their actual memory storage replicated only when their content is changed, possibly leading to an out-of-memory error when updating an element afterwards instead of during the copy operation. Implementation. Some programming languages delay evaluation of expressions by default, and some others provide functions or special syntax to delay evaluation. In Miranda and Haskell, evaluation of function arguments is delayed by default. In many other languages, evaluation can be delayed by explicitly suspending the computation using special syntax or, more generally, by wrapping the expression in a thunk. The object representing such an explicitly delayed evaluation is called a lazy future. Perl 6 uses lazy evaluation of lists, so one can assign infinite lists to variables and use them as arguments to functions. But unlike Haskell and Miranda, Perl 6 doesn't use lazy evaluation of arithmetic operators and functions by default. Laziness and eagerness. Controlling eagerness in lazy languages. In lazy programming languages such as Haskell, although the default is to evaluate expressions only when they are demanded, it is possible in some cases to make code more eager, or conversely, to make it more lazy again after it has been made more eager. This can be done by explicitly coding something which forces evaluation or avoiding such code. Strict evaluation usually implies eagerness, but they are technically different concepts. However, there is an optimization implemented in some compilers called strictness analysis, which, in some cases, allows the compiler to infer that a value will always be used. In such cases, this may render the programmer's choice of whether to force that particular value or not irrelevant, because strictness analysis will force strict evaluation. In Haskell, marking constructor fields strict means that their values will always be demanded immediately. However, neither of these techniques implements recursive strictness. For that, a function called deepseek was invented. Also, pattern matching in Haskell 98 is strict by default, so the tilde qualifier has to be used to make it lazy. Simulating laziness in eager languages. Python. In Python 2, x the range greater than print r 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, greater than print r 3. In Python 3, x the range is evaluated in the following example, so this is an example of lazy or deferred evaluation. Greater than r equals range greater than print range greater than print 3. This change to lazy evaluation saves execution time for large ranges which may never be fully referenced, and memory usage for large ranges where only one or a few elements are needed at any time. In Python 2, x is possible to use a function called xRange greater than print xRange greater than lst equals x for ex in r greater than print 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. From version 2.2 forward, Python manifests lazy evaluation by implementing iterators unlike tuple or list sequences. For instance, greater than numbers equals range greater than iterator equals iter greater than print numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, greater than print iterator less than list iterator object at 0x f7 e8 dd4c greater than print iterator dot next to sum Fibonacci greater than seq dot nth 1000 in c hash and bb net. The class system lazy less than t greater than is directly used. Public int sum equals greater than a plus b, a equals 3, b equals 5, return x, value, returns 8, or with a more practical example, recursive calculation of the nth Fibonacci number. Public int fib return 1, 1. Fib plus fib, public void main, int 10 equals int 32, pass, lazy less than int greater than fib equals new lazy less than int greater than fib, function is prepared, but not executed. Bool execute, if console writeline, execute equals y, else execute equals true, if console writeline, number is only calculated, if needed. Another way is to use the yield keyword.